Good morning. Today we're going to talk about something extraordinary, something that's all around us but we never think about, something that makes our very existence possible. Why don't atoms collapse? This is a question that puzzled the greatest minds in physics for decades. And the answer changed everything we thought we knew about reality. You see, according to the physics that explained everything from falling apples to orbiting planets, atoms should collapse instantly. If that happened, none of us would be here. The universe as we know it couldn't exist. But here we are. Physics had a problem. According to classical physics, an electron orbiting a nucleus should lose energy and spiral inward, just like a satellite losing altitude and crashing into Earth. The math was clear. The prediction was undeniable. Atoms should collapse in less than a billionth of a second. But they don't. This was more than just a scientific puzzle. This was a crisis. Everything we thought we understood about the universe was wrong. Something was missing, something fundamental. Everything changed. Between 1900 and 1930, a group of brilliant scientists discovered something that would completely transform our understanding of reality. Planck, Einstein, Bohr, Schrödinger, Heisenberg. These weren't just new theories, this was a revolution. They discovered that the universe doesn't work the way we thought it did. At the smallest scales, reality follows completely different rules, quantum rules. And these quantum rules, they change everything, not a particle. This is the first revolutionary idea. The electron isn't just a tiny ball orbiting the nucleus, it's something much stranger, much more beautiful. Think about the difference between a marble and a musical note. A marble is in one place. You can point to it, you can say, there it is. But a musical note? A musical note fills the room. It's everywhere at once. Electrons are more like musical notes than marbles. They're waves of possibility, waves of probability. And this changes everything about how we think about atoms. When something is a wave, it can't just spiral into a point. Waves spread out, they fill space everywhere at once. This is what an electron really looks like around a hydrogen nucleus. Not a tiny ball in orbit, but a cloud of probability. Think of it like a swarm of bees around a hive. You can't predict where any single bee will be at a given moment, but you know the pattern of the entire swarm. You know where bees are most likely to be and where they're less likely to be. The electron is like that swarm. It's not in one place, it's in all places at once, with different probabilities. And here's the beautiful thing. This cloud, this probability distribution, it's stable. It doesn't collapse, it can't collapse, because it's not a thing falling into the nucleus, it's a pattern, a standing wave. But there's more. Quantum leaps, here's the second revolutionary idea. Energy doesn't come in a smooth stream, it comes in packages, discrete amounts. Imagine a staircase, you can stand on the first step, you can stand on the second step, but you can't stand halfway between steps. You can't float in mid-air between the first and second step. Electrons are like that. They can exist at specific energy levels but not in between. They can jump from one level to another. That's what we call a quantum leap, but they can't exist in the spaces between. And here's why this matters for atomic stability. If an electron is already at the lowest possible energy level, it can't lose any more energy. It can't spiral down any further. There's nowhere to go. It's like being on the ground floor of a building. You can't fall any lower. Built-in fuzziness, the third revolutionary idea, is perhaps the strangest of all. Nature has built-in fuzziness. It's like trying to photograph a hummingbird. If you want a clear picture of where the wings are, their position, the image of how fast they're moving becomes blurry. If you want a clear picture of their speed, their position becomes fuzzy. You can't get both perfectly clear in the same photo. It's not a limitation of your camera, it's a fundamental property of reality. The same thing happens with electrons. The more precisely you try to pin down where an electron is, the less precisely you can know how fast it's moving, and vice versa. This isn't just a measurement problem. This is how the universe actually works. And this fuzziness, this uncertainty, it's actually what keeps atoms stable. If you could pin down an electron's position exactly, if you could say it's right here, then its momentum would become completely uncertain. It could be moving at any speed, in any direction. That kind of uncertainty would tear the atom apart. But nature doesn't allow that. The uncertainty principle creates a balance, a stability. Three quantum rules. Let me bring this all together. Three revolutionary ideas that work together to create something remarkable. Atoms that don't collapse. First, electrons aren't particles, they're waves, probability clouds that spread out around the nucleus. Second, energy comes in packages. Electrons can only exist at specific energy levels, not in between. Third, nature has built-in fuzziness. You can't pin down both position and momentum exactly. These three quantum rules work together like a three-legged stool. Each one supports the others. Together they create atomic stability. The wave nature spreads the electron out. The energy levels prevent it from spiraling down. The uncertainty principle maintains the balance. This is why atoms don't collapse. This is why we exist. This is why the universe is possible. Quantum all around us. Now you might be thinking, this is all very interesting, but what does it have to do with me? Everything. The device you are looking at right now, your phone, your computer, it works because of quantum mechanics. The screen, the processor, the memory, all of it depends on our understanding of how electrons behave in materials. LEDs and lasers, quantum mechanics, MRI machines that can see inside your body without surgery. Quantum mechanics, solar panels that convert sunlight into electricity. Quantum mechanics, GPS satellites that tell you where you are. They have to account for quantum effects to give you accurate directions. This isn't just abstract physics happening in some distant laboratory. This is the foundation of our modern world. Every time you turn on a light, send a text message, or take a digital photo, you're using quantum mechanics. The strange, beautiful, counterintuitive world of quantum physics isn't separate from our daily lives. It is our daily lives. Think quantum. The quantum world reminds us that reality is stranger and more beautiful than we ever imagined. Sometimes the most fundamental truths require us to think differently. For thousands of years, humans looked at the world and saw solid objects, clear boundaries, predictable motion. We built our intuition around the world we could see and touch. But the real world, the quantum world, is far more mysterious. It's a world where particles are waves, where things can be in multiple places at once, where the very act of observation changes what we observe. And yet, this strange quantum world is what makes everything possible. The stability of atoms, the chemistry of life, the technology that connects us. We live in a quantum universe. Every breath you take, every thought you think, every heartbeat, it all depends on the quantum rules that keep atoms from collapsing. So the next time someone asks you why atoms don't collapse, you can tell them, because the universe is far more clever, far more beautiful, and far more strange than we ever dared to imagine. Thank you.